Okay, so our first topic for general chemistry 2 will be on solutions. So I've said the keyword. I was supposed to ask you, um, what do all the photos you see have in common? Well, all of these are solutions. So we have salt dissolved in water, we have whiskey, orange juice, commercial vinegar, and milk of magnesia. So if you're not familiar with milk of magnesia, it's the medication for people who have acidic stomach or those with ulcers. So all of these are solutions, right? So let's go back to the definition of solutions. So solutions are homogeneous mixtures of two or more substances. So we distinguish between the two substances. So we have the solute, which is the substance that is present in smaller amount, and the solvent, which is the substance present in larger amount. So these are the definitions that you will see in your textbook. However, for example, what if we have 70% alcohol? Okay, so if I have 70% alcohol, which is the solute? Is it water and the solvent is alcohol because the alcohol is present in larger amount? Actually, no. Okay, so I don't prefer using these definitions. So I prefer these two definitions. So I have solute as the reactive substance and the solvent is the medium for the reaction. So the solvent is usually an inert substance. So water doesn't react with a lot of substances unless under extreme conditions. That is why water is considered as the universal solvent because all other substances dissolved in water retain their properties, their reactivities, while water, just remain like a wallflower. Okay, maybe that's a good analogy. So it's there, but it doesn't participate in any chemical reaction. So, if we're talking about solutions, we must also consider their concentrations. Okay, so I have here the label for the whiskey I showed a while ago. So, if for those who drink, okay, I'm sure you're familiar with alcoholic drinks having this label, this description of their label. So it says 88 proof. So 88 proof is actually an indication of the concentration of alcohol in your drink. So it's here 88 proof. On the other side, you see here 44% alcohol per volume. So proof is twice the percentage per volume of your alcohol. Okay, so for example, your San Miguel flavored beer is 3.5% alcohol per volume, so that is 7 proof. Okay, so what does this 44% alcohol volume mean? So for example, I get 100 ml of this whiskey. It means that 44 ml of it is alcohol. Okay, while the rest is just water and all the other components that you have in your whiskey. So there are, okay, so here's another example. This one is the IV drip that you see in hospitals. So you see here it says 0.9% sodium chloride on the label. So 0.9% sodium chloride. So if you look closely here, it has a description. It says each 100 ml contains sodium chloride USP 0.9 grams. Okay. So this one is actually weight per volume. Okay. Weight per volume. It means that if I get 100 ml of this IV solution, 0.9 gram of it is sodium chloride. Okay, so there are a lot of ways to express the concentration of solutions. By the way, when we say concentration, we are focusing on the concentration of the solute. Okay, so here are some of the concentration units that we have. So I've mentioned about the proof. We have weight percentage. We have weight per volume. I've mentioned this in the case of the IV drip. And then we have volume percentage. So this one is for the alcoholic drinks. Okay, so we also have what we call molarity, which I'm sure you've heard of in your Gen Chem 1. Then we have parts per million or parts per billion. So these units are usually used for solutes that occur in very, very, very low amounts. So if you've heard of news about water contamination, for example, of heavy metals. So they actually express the concentration of heavy metals in water in terms of parts per million or parts per billion. We also have molality, mole fraction, and normality. So most of these terms you're not familiar with, but don't worry, we will just focus on molarity. So by definition, molarity, symbolized by capital M, is just the moles of solute per liters of solution. So in symbols, we have here M equals N over V. Okay, so we have here a sample problem. So don't be overwhelmed by the problem, by the length. Okay. We have 1.46 molar glucose solution. So we write it as 1.46 m C6H12O6. So this solution contains 1.46 moles of the solute in 1 liter of the solution. Now, how many moles of C6H12O6 are there in a 500 ml solution of 1.46 molar C6H12O6? Okay, so we can do an intuitive approach here. So imagine we have here 1 liter of the solution. So the concentration is 1.46 molar. So we have 1.46 moles of glucose here. Now in the second solution, we have 0.5 liter. So this is in ml. So if you express it in liters, it will be 0.5 liter. It has the same concentration, 1.46 molar. So how many moles of glucose do you need in 0.5 liter of the solution to give you a concentration of 1.46 molar? So notice, okay, recall the formula or the definition of molarity. It's moles of solute over liters of solution. Notice the volume from 1 liter to 0.5, so it decreased by half. Do you think the moles will also decrease by half so that we still get the same molarity? Okay, so if we get the half of 1.46, that's 0.73 moles. Okay, so we're not sure if this is the correct answer, so we use the formula. So 0.73 moles of glucose divided by the volume of solution, which is 0.5 liters. And this actually gives us 1.46 molar. Okay, now there is actually a more mathematical approach to the problem. So it's asking for moles of glucose. If I have 1.46 molar or moles of glucose per liter of solution times 0.5 liter of solution. Okay, so I can cancel the unit liter, and then if I multiply 1.46 by 0.5, I get 0.73 moles of glucose. Okay, so that's pretty straightforward. Now, you also need to remember that there are two types of solute. Okay, there are molecular. Okay, I'm gonna write them down here. There are molecular solutes, and there are also ionic solutes. So I'm gonna give you a link to a video that explains clearly the difference between the two. So please watch it. Okay. So ionic solutes dissociate in solution. And dissociation means the cation and the anion of your compound separates from each other. So one example will be sodium chloride. So if I say I have 1 molar sodium chloride solution, I don't exactly have intact NaCl in that solution. What I have instead is I have sodium ions and chloride ions. So I have 1 molar sodium ions and 1 molar chloride ions in the solution. But on the label, we write it as 1 molar sodium chloride. Okay? So another example, barium nitrate. So if I say I have 1 molar barium nitrate solution, so this barium nitrate dissociates into barium ion and nitrate ions. Now notice in the chemical formula of nitrate, it has a subscript 2. So which means we can write the dissociation of barium nitrate in this manner. Okay, so it means that if I have 1 barium nitrate, I produce, okay, 1 what? Okay, let's say 1 mole. I have 1 mole of barium nitrate, and if I dissolve it in water, I produce 1 mole of barium and 2 moles of nitrate. Because per mole of barium nitrate, there are 2 nitrate units. Okay, so in our 1 molar barium nitrate solution, what we actually have is 1 molar barium and 2 molar nitrate. Okay, so let's try solving a problem related to ionic solutes. Okay, so how many grams of potassium dichromate, so the chemical formula is given here and also its molar mass, are required to prepare a 250 ml solution whose concentration is 2.16 molar. So it's asking for the mass of potassium dichromate given that the solution has a concentration of 2.16 molar or 2.16 moles per liter. Okay, now we're given the volume of the solution, which is 250 ml, and if we express this in liters, it's 0.250 liters. Okay, and then this one pertains to the moles of potassium dichromate, right? If I want to get the mass of potassium dichromate, I'm going to use the molar mass. So 294.2 grams per mole of potassium dichromate. So this unit cancels and this unit also cancels, and I end up with grams. So using your calculator, we get a value of 158.87 grams of potassium dichromate. So this means that, okay, so I get 250 ml or 0.250 liters of water. Okay, and then I add solid potassium dichromate here, and this one has a mass of 158.87 grams. I stir the solution and then I get my 2.16 molar potassium dichromate solution.